All right, here's an example. We're going to do an example of a key, and then in the same video, using the same problem, trying to find a pin. Okay, so we have a chain sprocket that delivers 110 horsepower to a shaft at a rotational speed of 1700 RPM. The sprocket has a bore diameter of 2.5 inches, and the hub length is 3.25 inches. All right, so I've kind of already set this up for you, given the power, the RPMs, the diameter of the shaft, length of the hub. We're going to use a design factor of 2. That's what N is. We're going to find the minimum dimensions, but also the width and height. Okay. We're going to use SAE 1018 cold drawn steel. It has a SY of 50,000 psi. Okay. Now, first thing, we do our given sketch properties. We can actually, in the properties, find the width and the height of this key. All we need to know is the shaft diameter. So we scroll over to this table right here. And over here is shaft diameter. We're in between 2.25 and 2.75. So we go ahead and use this. So we can use a 5/8 width and height. So boom, those are already done. And again, this key is going to go into that sprocket to hold it into that shaft. So let's go ahead and find what we need. So solution. Do solution underneath find. So let's find L min. Okay. So L min equals 4Tn over dWsy, which is also equal to 2T over tau d dW. All right, because we're designing based on the failure. Okay, if you remember, find TD, that was equal to 0.5 times SY over the design factor. Okay, so that's why those two equations work. And we're going to assume that because the problem doesn't give us the material of the sprocket or the shaft, so we're just going to use that one equation that states that this has a lower material property. Okay. All right, so let's go ahead and plug this in. 0.5 times 54,000 psi over design factor, and we get this tau d to be 9,000 pounds per inch squared. Now we're going to look for the torque. Find T. Torque is equal to the power over the RPMs. So 110 horsepower. Got to convert this. There's 550 pound-foot per second in 1 horsepower. Okay. 1 HP. Then we're going to convert this to inches. I'm going to divide by the RPM, revolutions per minute. We need to convert that. 1 minute, 60 seconds, and there's 2 pi radians in 1 revolution. So the torque is 4,079 pound-inch. Okay, from this chain sprocket. All right, now we can plug them in. L min equals 2 times 4,079 pound per inch over 9,000 pound per inch squared times 2.5 inches times 0.625 inches. And we get L min to be 0.58 inches. That's the minimum. Now, I recommend probably between 2.5 and 3 inch when you make it to keep it consistent with the hub. Okay? All right. Awesome. So that's an example of how to size a key, all right, for a sprocket. Now we're going to go use the same problem, but we're going to design a cylindrical pin to transmit the power. Okay, but we're going to design it so that it will fail in shear if the power exceeds 220 horsepower. Okay, so I set it again up. Power 1 is 110, power 2 is 220, diameter of the shaft 2.5. We have an RPM of 1700. We're going to use, again, SAE 1018 SD steel for this pin. We got SY, which is your yield, 54,000, and then our ultimate 64,000 KSI. All right. Because what we're going to do is we're designing this, okay, so that these two rules, okay, that tau 2 is your ultimate shear stress. All right. So in failure, so failure analysis, then we can follow these rules, okay? That for the 220, we're going to use the ultimate stress times 0.75 over our design factor. Okay, we're going to use actually 1 for now. I have an Excel sheet that does different properties and different design factors that I'll show you, okay? But also that T1 will be, we want to make sure that it's right at the yield or below, okay? So it's going to be SY times 0.5 over N. Again, these equations are not tabulated, these shear stresses, but we use equations and failure equation based on these values here, okay? So we're going to assign tau 2 to be SU times 0.75, okay, over the design factor, and then we want to make sure that that diameter that we find, okay, so we're going to find diameter. We'll call it diameter, that's fine, D, that it satisfies both of these conditions, okay, because it will fail and shear at 220, but it will also satisfy that it will yield, okay. All right, so let's go to the solution. So design failure conditions. So pin should not yield at T1, okay, and the pin should shear at T2, okay. So basically I'm going to just say tau A just for now is less than or equal to the ultimate shear stress, but it's equal to what I had above, 0.5 times SY over the design factor. And then this, I'm just going to call it tau B right now, the ultimate shear stress. This is SU times 0.75 over the design factor, okay. Then, based on the stuff we were learning, tau for the pin, okay, so shear stress for pin is 4T over D of the shaft times pi D squared, okay. So in this equation here, we're going to use the tau B or tau 2 if you want to call it, okay. So this is kind of like tau 2, and this will be tau 1 eventually, and I'll show you how this works. So let's rearrange this equation for D2, which will be right here, okay. This is the diameter using tau B or tau 2, the torque 2 or power 2, all right, we can find it. So D2 is 4 times the torque at 2 times divided by the diameter of the shaft times pi times this tau B, which I'll call it tau 2, Okay. And I'm just going to use a design factor of 1 for now. So let's go ahead and plug this in. 4 times. Now we haven't found the torque. So let's go ahead just over here. I'll find it for you. Actually, you know what? Let's keep it consistent like I have been doing. Let's find, oh, that color's hard to read. Let's find the torque at 2. Okay. So T2 is just like we did before. It's going to be the power over 2 over the RPMs. And I'm just going to skip the units just to save some time. So 220 times 550 times 12 over 1700 times 2 pi over 60. All right. Again, we're converting them. So the torque at 2 should be 8,156 pound-inch. Okay. And if you remember, T1 was 4078 pound-inch. Okay, that was from the previous problem. All right, so we have those. Now we can find this. So D2 square root of 4 times the torque, 8156 pound per inch, over the diameter of the shaft, which is 2.5 inches, times pi. And then this tau 2 is tau b, which will be SU, which is 64,000 psi times 0.75. Again, designing for failure, design factor. Okay. The design factor was 1, so I'll just divide by 1. The diameter, 0.294 inches. Okay. So using this design, this rule for design factor up here, where you take your ultimate stress times 0.75 over your design factor, okay, so it'll shear, okay, then this is the diameter that you need. Okay, so it will shear when it reaches that much stress. Okay, now we also want to make sure that that diameter satisfies this, okay, so it doesn't yield at that. So how do we do that? Well, we need to check. So what we're going to do is we're going to find tau A, and we'll check that. Okay, so tau A was SY times 0.5 over the design factor. So this is 54,000 times 0.5 over 1, and you get 27,000 pound per inch squared. Right? Okay, now let's check to see if tau 1 is greater than or equal to tau A. And tau 1, we use the same equation because it's a pin, 4 times T1 though, over diameter of the shaft times pi times this diameter that we just found. Okay, so tau 1, 4 times 4,078, the power converted to torque, right? 2.5 inches times pi times 0.294 inches squared. Tau 1 becomes 24,028 pounds per inch squared. Okay, so we need to compare this to that. And this number is lower than that, so we are good. Okay, so that's what we're designing. All right, we wanted to make sure that this will satisfy both conditions. So we'll shear when it's 220, and we won't yield at 110. All right, now, so what I ended up doing was, it makes it a lot easier if you want to look at comparisons. So I made an Excel sheet, and this is what I want you to do. Okay, so let's just look first over here. All right, so I have nomenclature. So yield, strength, and shear, power, diameter, RPMs. You got that, nomenclature. Now here's my givens. We're using a cylindrical pin, the power, and then I converted it to pound-foot per second. Power 2, converted that. Diameter of the shaft, RPMs, design factor. Down here, properties. Okay. All right, we have pretty much SY. Okay. Oops. This should be, sorry, this is SY. I was doing something SU. Okay. I'll fix, yeah, don't worry about those. That's okay. All right. And then this is your tau 2 that we talked about. Tau 1, right? Our rules for designing. Okay, so we have 48,000 for tau 2, 27,000 for that. Then the solution is down here. Okay, so I converted the RPMs to omega. Here's our torque 1, our torque 2, and then I found the diameter, okay, based on our tau 2 that it's above. And then I checked. Okay, I wanted to make sure that this was lower than this number. Okay, so it's green. So let me just fix these two here just to have it complete, in here, and I'll go through some of these. So let me zoom out a little. There we go. Okay, so sorry about that. So here is the problem that we just did. Okay, what I did it over here, the next one, is I just changed the design factor to 3. All right, so our diameter got bigger, right, which makes sense, and we're still good. This is less than tau 1. And again, the rules we're following are standard failure rules for shear, okay, where you take your ultimate stress, you multiply by 3/4, and then your, for yield, so it doesn't yield, you take your yield strength and you multiply by 0.5, okay. So properties, now, next one I did was aluminum, design factor of 1, and this will not work, okay. This will actually yield at 100, like at 110. So that aluminum will not work, okay. And then back here, what I ended up doing is a different material, SAE 8630, and this one also works, okay. Now, again, what I would do is you do these case studies, right, and then you put a price, all right, and see, okay, does it cost, which one's going to cost the company less money and still get the job done, right? This is like almost a 1/4 inch, where here you got to go a little bit bigger. Is it going to cost you more, right? The material, the manufacturing time, and all of that, shipping, everything, okay? So here's a quick, cool little Excel that shows how you can pick and choose the material you want and when things will break. Overall, I showed you in this video how to design a key and then how to design a pin. All right. If you have questions, let me know. Thank you.